Welcome to this presentation on high-performance CMOS clock distribution. I'm Tony Chan Carusone, a professor at the University of Toronto, and this presentation summarizes some work done by Junjun Mo in my lab. We'll begin with a brief background about the importance and challenge of distributing a high-performance, high-frequency clock across a chip, and then we're going to review some of the sources of jitter: power supply-induced jitter, random jitter, and jitter amplification, and look at how each can be modeled in full-swing CMOS clock distribution circuits. With these analysis, I'll then arrive at some design considerations for full-swing CMOS clock distribution circuits. And finally, I'll briefly discuss an example design done in a 16-nanometer FinFET technology. Because the power and area required to generate a high-frequency precise clock in modern high-performance integrated circuits, it's common to have one precision phase lock loop generating a clock and then share the output from that PLL across multiple lanes. For example, you might have multiple analog to digital converters running off a single PLL clock. In such cases, the clock has to be distributed a significant distance around the chip, often hundreds of micrometers, and this creates a series of challenges. First of all, the clock has to be repeated with buffers periodically, depending on the length of the clock distribution, and these all consume power. They also introduce timing uncertainty in the form of random jitter, duty cycle distortion. Power supply noise can introduce jitter, power supply induced jitter, or PSIJ. And the sum of all these extra jitter sources can approach or even exceed the timing uncertainty that arose in the clock generation circuitry, the VCO or PLL. Moreover, all these buffers consume a significant fraction of modern high-speed integrated circuit power in some cases. As data rates increase and sampling rates get higher, the jitter budget tightens and clocking power further increases. So all this clock distribution circuitry is absolutely critical to the design of such systems. Several approaches have been taken to high-performance clock distribution. Current mode logic, or CML, clock distribution and resonant clocking have both been used with great efficacy. CML clock distribution makes use of differential pair-based buffers, whereas resonant clocking uses passive inductors to help efficiently amplify high-frequency clocks, even in the presence of large capacitive loads. However, recently CMOS clocking has been increasingly used for the distribution of very high frequency and precise clocks. There's a number of reasons why we might be interested in CMOS clock distribution. First of all, the circuits consume only dynamic power. There's no DC bias currents required, and therefore there's no biasing circuits required. This makes their design really simple. The buffers can be inserted wherever they're needed without the need for routing bias circuits or anything like that. CMOS inverters provide full swing clocks with fast rise fall times, and that's good for low jitter clock distribution. They also offer the potential for dynamic power scaling. Inverters are broadband, they can be used for any clock frequency, and as clock frequency comes down, power consumption decreases proportionally. So these can be very power efficient when you have to operate the clock distribution over a wide range of frequencies where resonant clocking fails. The circuits are very simple, and we know they're going to scale well in advanced CMOS technologies because the CMOS inverter is, of course, ubiquitous in digital logic and memory. The main drawback for CMOS clock distribution circuits that's cited is that CMOS inverters both create power supply noise and are sensitive to it. They introduce large transient currents onto the power supply that can disturb the supply voltages, thereby affecting neighboring buffers and neighboring critical circuits. And any supply noise modulates the delay through an inverter and thereby creates jitter at its output. So that's why we're going to spend particular attention on power supply-induced jitter. So next, let's take a look at power supply-induced jitter in CMOS clock distribution circuits. As we just mentioned, supply fluctuations introduce jitter in CMOS inverter buffers by modulating gate delay. So that's just illustrated here in this cartoon. As the supply comes down, we have a slower rise time, and therefore we see some extra delay introduced. And if the supply is moving back and forth, as illustrated here, then that's going to show up as jitter. When supply noise is small, it turns out that The gate delay variation is proportional to the magnitude of the supply noise. So that is, for a change in supply voltage, delta VDD, we see a proportional change in gate delay, delta TD. And here's an example simulation that shows that that's indeed the case. This is done in a CMOS technology with tens of millivolts of supply noise, which is pretty typical in an integrated circuit. Now, if we adopt a simple model of the delay through an inverter where we consider a step input with zero rise fall time and consider the time it takes for that step input to propagate to the output, it can be shown, adopting some simplifications, that the sensitivity of the CMOS clock buffer to power supply noise is a constant percentage uh, of delay variation for each percent of supply variation. You can write this analytically as shown here, where basically the fractional change in the gate delay is proportional to the fractional change in the supply voltage. And the constant of proportionality here, K, is independent of the CMOS buffer size and the cap load. If you have a smaller buffer or larger cap, gate delay increases, and the delay variation will also increase for the same amount of supply noise in proportion. So if we wanted to use this model to predict the amount of power supply induced jitter, we'd first have to find the amount of power supply noise, the variation in VDD. And we could do that by first having a feel for the transient currents that are being drawn from VDD and multiplying that by the impedance of the power distribution network. And we should always keep in mind that that impedance is probably frequency dependent. Specifically, there's likely to be large decoupling capacitors on there, which reduce the impedance at high frequency. So the frequencies of the content of the transient currents important here. And then using the model shown on the last slide, we know that the induced jitter, the variation in gate delay, is going to be proportional to the gate delay with no variations times the percentage VDD variation. Now it turns out this constant of proportionality K, which essentially quantifies the power supply sensitivity of the buffer, is essentially a technology constant. It's related to the supply voltage used and the threshold voltage of the constituent devices. Now, of course, the PMOS and NMOS threshold voltages may differ, and these may affect the rise and fall times differently. But in any case, K is essentially a product of the technology that's being used for the inverters. So how does this affect the design of our CMOS clock distribution? Well, if we imagine that these CMOS buffers are sharing a common supply voltage, and let's consider the case where the power supply noise that each of them sees is highly correlated with each other, which may not be the case, by the way, if these inverters are widely spaced across a chip. But if that is the case, then it's clear that the power supply induced jitter will accumulate along the chain of buffers. If the supply voltage goes up, all the inverters will get a little faster and the clock edges will arrive earlier. Supply voltage droops a little bit, all the gates will get slower, and you'll see the edges delayed a bit. So to try to mitigate the accumulation of power supply induced jitter across a global clock distribution network, we want to minimize the number of buffers along the chain. We also want to make sure that we maintain sharp edges, transition times, because we see that in this expression that the variation in gate delay is proportional to the rise fall times. And clearly, anything we can do to keep the supply voltage constant, supply regulation would be very helpful, even just a lot of decoupling capacitance. And then finally, a higher supply voltage and or lower supply voltage would benefit this technology constant, K. Next, let's look at the random jitter introduced by noise in these CMOS clock buffers. So the random jitter that's contributed by CMOS inverter is originating from the intrinsic thermal noise from the MOSFETs in the inverter during the rise and fall transitions. We focus on thermal noise here because flicker noise doesn't really have time to accumulate during this very short transition time. So the random jitter from an inverter with a drive current I and a time delay TD will be proportional to TD over I. It's proportional to TD because the slower the rise fall time, then the same amount of noise is going to give rise to more timing uncertainty. And it's inversely proportional to I. Way you can recognize that is by seeing that even with the same time delay, if the time delay is the same, but you increase the current flowing through these transistors, then the thermal noise current represents a smaller fraction in a sense of the total drive current through the transistors. So you end up with less total jitter added. Now, again, in a clock distribution network that comprises N series inverters, because the random jitter introduced by each inverter is going to be statistically independent from its neighbors because each is arising from the thermal noise in its own transistors, we see that random jitter accumulates not in proportion to the number of buffers, but in proportion to the square root of the number of buffers. Nevertheless, a lot of the same design tips that we saw for mitigating PSIJ also apply to reducing the accumulation of RJ along a chain of inverters. We want to maintain sharp edges. That's going to give us a smaller TD. And we're going to want to use bigger buffers. Larger I is going to give us less RJ introduced by each buffer. That's going to cost us more power, of course. And we're going to want to use fewer buffers. That's going to reduce the number N of buffers along which the RJ can accumulate. So although RJ can be significant in a long chain of buffers, in our experience, this is rarely the primary source of jitter in CMOS clock distribution networks. Usually more jitter is contributed by PSIJ and or from the accumulation of RJ. And that's what we're going to talk about next. We're going to talk about jitter amplification, which is really the magnification of input jitter that arises in a buffer. So we're going to define jitter amplification along a chain of buffers as the ratio of the input jitter to the output jitter at a certain point of the clock distribution network, for example, the far end over here. So that's going to give us a constant jitter amplification factor. Jitter amplification arises from the transfer characteristic of the clock path without considering any other jitter sources such as power supply noise or thermal noise of the buffer. So just to be clear, even if there's absolutely zero noise in the transistors of this buffer and there's zero power supply noise, if there's jitter at the input to the buffer chain, you will see more jitter at the output of the buffer chain. And that's just because of the finite bandwidth or the finite rise fall times of these buffers. And that's jitter amplification. A good way to understand and model jitter amplification is by considering the jitter impulse response of a clock distribution network. So consider, an ideal clock waveform shown here with a solid line, but then instead consider perturbing one of the clock edges by delaying it, only one. That will obviously result in a perturbation in the transition of the corresponding edge at the output of the clock distribution network, but in fact, it will also perturb subsequent clock edges. Now, the type of perturbation shown here is, a delay in the input clock falling edge, resulting in a delay in this falling edge, but an early arrival of this rising edge, and then a late arrival of the following falling edge, and so on. So we can define the jitter impulse response by quantifying these time variations in the output of the clock distribution network and plotting them in a discrete time plot as shown here. So in this particular case, the jitter impulse response results in a late transition here, then early, late, early. So you get this kind of impulse response that's high pass in nature. Now, for small perturbations in input transition times, such as are likely to arise due to RJ or PSIJ at the input to a clock distribution network, we can consider the input-output phase response of the clock path to be linear, so that for any arbitrary input jitter, the output jitter sequence is just the convolution of the input jitter sequence with this jitter impulse response. So here we're showing some exemplar input and output waveforms from a simulated clock distribution network where we're introducing an input jitter impulse and looking at how that propagates across several clock edges at the output of the clock distribution network. This clock distribution network has 5 stages, and has a fairly slow rise-fall times formed by the resistance and capacitance of the clock distribution network at a clock frequency of 10 gigahertz. So as a result, when we introduce a jitter impulse at the input to the clock distribution network, it impacts the corresponding falling edge at the output, but also you see the next rising edge comes early. And so this is typical when we have incomplete settling of a clock edge. The falling edge doesn't get all the way down to the bottom, so the next rising edge actually comes early. And as a result, it's kind of got a head start on the way up compared to the ideal waveform in orange. So it actually ends up higher than the orange one, and then the following one is a little bit late, and then the impact essentially disappears here. But this is a typical illustration of what can happen in CMOS clock distribution networks when you don't have complete settling of the clock waveform at the output of each buffer. Then jitter impulses propagate across multiple clock edges, and you get this sort of high pass jitter impulse response. On the other hand, when CMOS clock buffers have rise-fall times that are much less than half the clock period, there's virtually no jitter amplification. And that's what's shown here, right? Even with the jitter impulse introduced, there's complete settling before the subsequent rising edge. So the jitter impulse simply looks like a jitter impulse. Here, we put in 5 picoseconds of jitter, we get out 5 picoseconds of output jitter just on that one edge. Now, when the rise-fall time of the CMOS buffers don't allow for complete settling, that's when we get this ringing style of jitter impulse response that we saw previously. So here, 5 picosecond input jitter impulse results in even more than 5 picoseconds delay in the falling edge, and then we get an early edge and then a late edge and so on. Now, we can actually take the Fourier transform of this jitter impulse response and get a jitter transfer function, which shows us how different frequencies of input jitter, or rather how different input phase noises are amplified across different frequencies. So essentially the input phase noise here is shaped by this jitter transfer function of the buffer. And again, with a ringing style jitter impulse response, it's likely to be high pass, which means there's almost no amplification of low frequency jitter, but high frequency jitter, in particular things like duty cycle distortion, are significantly amplified. So clearly, the overall amplification of RJ is going to depend on the spectrum of the input RJ phase noise. So here's an example where we're showing the jitter amplification factor that we defined a few slides ago. It's just one number that relates the input and output jitter, RMS, of a clock buffer or a chain of buffers. And we're sweeping on the x-axis here the bandwidth that contains 90% of the RJ. So essentially we're taking white RJ and then low pass filtering it with different bandwidths. And as we increase the bandwidth of that filter, we're introducing at the input to the buffer chain more and more high frequency jitter. What we see as we introduce more high frequency jitter, we get a larger jitter amplification ratio because it's really only the high frequency jitter that is being amplified in this case. So now that we've got the requisite background in how jitter is introduced and amplified along CMOS clock distribution networks, let's come up with some design considerations for full swing CMOS clock distribution networks. So let's look at this by way of example. Let's consider the case where we need to distribute a 10 gigahertz clock in 16 nanometer CMOS across a total distance of 2 millimeters across a chip. And let's say we need to tap off that 10 gigahertz clock in 10 places. Let's say there's 10 samplers that need to use that clock. And let's say they're equally spaced, 200 microns apart across that 2 millimeters. Now, when we're designing the global clock distribution network here, we have some choices. We can either have fewer buffers, each distributing across a longer distance, or more buffers repeating the clock more frequently. So in these examples, when we talk about having only two stages, we've only got two buffers, and each one drives a 1 millimeter interconnect, or we can have 5 stages, each one driving a 0.4 millimeter interconnect, or 10 stages, each driving a 0.2 millimeter interconnect, and so on. And we're going to observe the jitter at the outputs of each of these local buffers at each of the 10 tapping points and see what happens. So on this slide, we're looking at the PSIJ and the RJ, and in both cases, as we sweep across the x-axis, the number of buffers that we've used to distribute across that constant 2 millimeter interconnect. And in both cases, we're plotting the worst case jitter that's observed at any of the 10 tapping points along the global clock distribution network. Now, looking at these plots, we see some trends that we expected based on our preceding analysis. First of all, as we increase the size of the buffers from 28 fingers to 32 to 36, we see we're using more power, but both PSIJ and RJ improve. We also see that PSIJ consistently degrades as we introduce more and more buffers, and that's because PSIJ can accumulate over more and more buffer. Each buffer, in a sense, introduces a little bit more PSIJ. For RJ, the situation's a little more interesting. As we go from 2 to 5 stages, adding more buffers means that each buffer is driving a shorter distance of interconnect, so the edge rate sharpens, we get faster rise fall times, and we saw that that reduces the RJ contributed from the local buffers. But if we go further and start introducing even more buffers, 10 and 20 buffers, adding those extra buffers doesn't really improve the edge rate much. But now we've just got more buffers, each one accumulating a little bit of uncorrelated RJ. So we've got that square root n dependence as we see the accumulation of more RJ across more buffers. So there's kind of a sweet spot here for RJ. But again, in a lot of cases, the RJ introduced by the buffers themselves is less than other sources of jitter. Next, we want to look at jitter amplification. Now, the situation here is a little bit more complicated, and that's because across a chain of inverters, we're going to see amplification not just of the jitter at the input to the entire chain, but also RJ or PSIJ introduced by the first stage will be amplified by the second and subsequent stages. And second stage jitter will be amplified by the third and subsequent stages, and so on. So we'll see that if jitter amplification arises, it can very quickly dominate the overall jitter picture here. So to look at these trade-offs, in this case, we're going to consider only one global clock buffer stage, and we're going to maintain constant sizes on these buffers and a constant spacing between the intervening local buffers that are tapping off 200 microns apart. And we're just going to vary the interconnect length here between global clock buffer stages. So we may start out at 200 microns and then go to 400 microns to 600 microns and see what happens as we sort of repeat the global clock less and less often. We're going to introduce RJ at the input and observe the RMS jitter at the output of the local buffers. Okay, and we're not going to have any transient noise turned on in these simulations for any of the buffers themselves. So the only jitter that we observe at the output here, there'll be no power supply noise either. The only jitter we observe here will be due to the amplification of the input jitter. So if we introduce a 10 gigahertz clock with white RJ at the input, and start increasing the wire length per stage, we see absolutely no jitter amplification arising until we get up beyond about 1 millimeter of interconnect per global clock distribution buffer stage. And then we see the jitter amplification factor increases precipitously beyond that. Now, if we increase the clock frequency to 14 gigahertz, we see that the jitter amplification starts arising at shorter lengths of interconnect. And that makes sense because with the higher clock frequency, the half period is shorter, so the rise fall times of the clock have less time to settle before the next edge arises. Now keep in mind this is just for one stage of clock distribution, so the second stage will amplify any RJ introduced by the first stage. So this type of jitter amplification will accumulate quickly along a chain of buffers and essentially really needs to be avoided. So the onset of jitter amplification sort of, in my mind, represents an upper limit on the clock frequency at which your clock distribution network can be used. So let's summarize our design recommendations here. Again, assuming you've got to distribute a clock across a fixed distance and across multiple target circuits, how should you design the clock distribution network? Well, first of all, to minimize the number of buffer stages, take the longest possible distance between buffer stages that avoids reflections. Remember that fewer buffers improves PSIJ and provides less accumulation of RJ. But if we make the distance between stages so long that we start seeing reflections of the high frequency clock rattling around between buffer stages, then that's going to slow down the rise fall times and start leading to jitter amplification. So that's got to be avoided at all costs. That forms the sort of upper limit on the distance per stage. Having established the distance per stage, we're going to size the buffers to ensure the fastest possible rise fall times. Remember, the fast rise fall times and complete settling of the clock waveform are good for all aspects of jitter performance. On the other hand, oversizing the buffers can reduce their RJ somewhat, but since that's rarely the main limitation, it's generally a waste of power to do so. The local buffers themselves, they can be sized to strike a balance between the cap loading they introduce onto the global clock line, which may in turn slow the rise fall times here, and the RJ that they themselves introduce. Remember, a larger local buffer will introduce less RJ itself. And of course, ultimately they have to be sized large enough to drive whatever capacitance the sampling circuit needs presents as a load. Finally, I'll just take a quick look at an example design done to try and quantify some of these effects. So in this design, two test cases were considered. Both distribute a clock across a total distance of 2 millimeters and have 5 tapping points. In case 1, there's 10 repeaters along the way. And in case 2, there's only 5, but the 5 stages are sized somewhat larger. So these correspond to the two design points indicated here with the black and red circles. So our expectation is that using fewer buffers will help, and that we can size up the buffers since we've got fewer of them and still burn less power than what we're burning in case 1. So this is, I think for some people, counterintuitive, that you're actually better off with pumping more power into fewer buffers. You're going to win in terms of PSIJ, RJ, and as long as you avoid jitter amplification, it's all good. So here's a summary of the simulated results. We see that as expected, with only 5 buffers, but sizing them larger, we get significantly less PSIJ accumulated along the chain of buffers. And we also see a little bit less RJ, but the amount of RJ is quite small in both cases. And importantly, we see essentially no RJ amplification in either case. This is critical, so that even with the 5 buffer clock distribution, the distance per stages is still short enough that reflections don't appear. So we've introduced 150 femtoseconds RMS jitter at the input to the clock distribution here. We see basically no amplification of that in either scenario. So we managed to save about 20% of the power here and actually improve the jitter performance, especially with respect to PSIJ. Here's a die photo and layout plot of the test chip. It's fairly simple. There's just 2 clock paths here that we can multiplex and look at the output, the 2 test cases. We've also got circuits here to introduce power supply noise so that we can measure PSIJ of the chain. Measurement of PSIJ is actually quite complicated. We need a number of sort of auxiliary circuits to be able to do this. We've got a really simple circuit that we can use to introduce large transient currents onto the supply and thereby introduce some noise. But when we do so, we don't know exactly how much noise is arising unless we observe it. So at low frequencies, we make use of a so-called spy hole that allows us to probe the power supply noise on the board through a high impedance path to the power supply distribution network. But because that's a high impedance path, that's only good for very low frequency power supply disturbances. For high frequency power supply disturbances, we need to make use of a buffer that's been integrated on chip. We AC couple the buffer, so therefore we can't use that for the low frequency measurements. Here's a preliminary summary of the PSIJ measurements. These are taken at 3 points along both test case 1 and test case 2, right, of global clock distribution. And we see that the 5 larger global clock buffers are giving rise to less power supply noise than the 10 buffer case, which burns more power. So there is some jitter observed even with no supply noise introduced, so we take that as a baseline and we see that that's constant along the clock distribution network. That's probably just arising from measurement sources of jitter and is the same both in case 1 and case 2 at about 3.7 picoseconds peak to peak. But that as we introduce PSIJ, we start seeing extra jitter added on top of that, and it accumulates as you proceed down the chain. But it accumulates to a much higher value when we've got 10 buffers than when we have only 5, as we expected. So I hope you enjoyed that quick tour of CMOS clock distribution. It's an increasingly popular technique for the distribution of high performance clocks on integrated circuits.